Welcome to the STEM Sessions podcast. I am your host, Jarl Cody. I watch numerous outdoorsy type YouTube channels. I'm always looking to increase my knowledge and skills of the outdoors, knots, navigation, gear reviews, new areas to explore, first aid, etc., etc. Well, back in August, Dave Canterbury posted a video entitled Secrets to Accurate Land Navigation, the link to which is in the show notes. He discusses how the distance you measure on a map is not the same as the distance physically traveled because of changes in elevation along that path. A fact Dave claims is excluded from most navigation classes, yet it's critical to successful navigation by map and compass. Now, I've taken many navigation courses, and Dave is correct in that distance deviations due to elevation change is typically not mentioned by the instructors. I mean, classes are typically taught on flat ground, so there's really no need. But I think he overstates their importance, at least for the use cases in the meaty part of the bell curve. Of course, being an engineer, I needed to prove this to myself. And the following episode is the results of that deepish dive into the topic, and it's a good example of basic math being relevant in the real world. This is the STEM Sessions Podcast, episode 21, What a Distance Slope Makes. A few months ago, I watched a video discussing how a change in elevation causes your distance traveled to deviate from the distance on a map. Basically, if you're walking uphill or downhill between 2 points, you walk a greater distance than if those points were at the same elevation. The main point of the video was you need to track this deviation during land navigation with a map and compass because it will add up over the course of your travel and throw off your route. Now, the engineer in me says while this is mathematically true, it probably doesn't matter because the deviation is minimal in circumstances most people will find themselves in. In fact, I remember having similar discussions on the trail 20 years ago when handheld GPS receivers first hit the consumer market. I carried one before most people did, so I'd always get questions about how they worked. One guy asked if it took elevation change into account, and I told him it tracks elevation as its own parameter, but I wasn't sure if it accounted for change in elevation's impact on your distance traveled. But again, I said for most hikes it didn't matter. The math behind this discussion is the Pythagorean theorem. In a right triangle, the square of the length of the hypotenuse is equal to the sum of the square of the lengths of the other two sides. And when it comes to navigation, here's how this theorem would apply. So think of a piece of graph paper. The 0, point, or the origin, is where we are currently standing. The x-axis represents the distance shown on the map between our origin and our destination. Let's say the map shows a distance of m, just for simplicity, m for map, to our destination. So we draw a dot at coordinate m0 representing this distance. The y-axis represents elevation change, and let's say the map shows our destination to be at an elevation of e compared to our origin destination. And we draw a dot representing the elevation of our destination at coordinate me. Now draw a triangle connecting the 3 points. It should be a right triangle, so the Pythagorean theorem applies. The distance we will physically travel between our origin point, 0, and our destination point, me, is the hypotenuse of that triangle. Let's call this distance d. It's obviously longer than the distance measured on the map, which is m, because of the elevation change, e. And obviously for this all to work, elevation and distance need to be in the same units. So plugging all those variables into the Pythagorean theorem, and we get the distance we physically travel, d, is equal to the square root of the quantity m squared plus e squared. Therefore, the bigger the elevation change, the more physical distance deviates from your map distance. Now, the YouTube video I was watching approached its argument from the perspective of cross-country and off-trail navigation using a map and compass. You find your current position and destinations on a map, you determine the distance between them and the direction of travel. Then you divide the journey into segments you can count or pace, say 100 feet, 100 meters, or zero point 0.1 miles, just to name a few. As you travel, you manually keep track of the distance you've walked, and there are several ways to do this, and I plan to make a separate episode about the math behind it. But at the end of the first segment, you stop and update your course, and then travel to the next segment. To account for the difference between map distance and physical distance, the YouTube video also uses the Pythagorean theorem, and it's laid out in a similar fashion as I just did. To calculate the squares and the square roots, the video says to calculate them in your head, or use the calculator app on your phone, or use a pre-printed lookup table in your navigation notebook. For me, only the last option is acceptable. I mean, what if your phone battery is dead, or what if you lose it? And how many can do squares and square roots in our heads while tired and stressed? And would I even trust the results? And really, let's be honest, how many of us know how to do square roots in our head in the first place? So is there a threshold below which we don't need to worry about this deviation in distance values? And for the instances when we shouldn't ignore it, is there a shortcut or rule of thumb we can use to avoid calculating squares and square roots by hand? To answer the latter question, we need to relate elevation E to map distance M, because those are the only two known quantities we can rely on. So let's go back to our triangle plotted on graph paper. Elevation E would be the rise of the triangle, and map distance M would be the run of the triangle. The slope of a line is defined as rise divided by run, so in our case, the slope of that hypotenuse is the ratio between elevation and map distance. And I think slope is a good starting comparison because ratios are often easy to estimate without a calculator or complex division. When you're comparing two numbers, you can quickly determine if one number is about half the other, or 10% of the other. And when you have those two estimates in mind, you can combine them to make other estimates. 25% is half of 50. 60 is just 50% plus 10%, and so on. Physically speaking, the slope represents the steepness or the incline of the path. Let's say our elevation E is 2 feet, and our map distance M is 10 feet. The slope is E divided by M, or 0.2. So for every 10 units of map distance, elevation increases by 2 units. If M extrapolates to 20 feet, E would be 4 feet. This would be considered a 20% incline or grade. But note, neither the ratio nor the incline equals the angle of the triangle. At the opposite extreme, a slope of 1 means for every 10 units of map distance, elevation increases by 10 units. It's unit for unit parity. So a slope of 1 is a 100% incline, and when pictured on the graph, this would be a 45-degree angle. Here are a few real-world reference examples to help us conceptualize this. Wheelchair ramps will typically have a slope of 1 to 12, or 0.08 or 8%, which is a 5-degree incline. U.S. interstate highways have a max grade or incline of 6%, or about 1 to 16.5, which is a slope of 0.6. Train tracks will have a grade of 1.5% to 4%, which is 1 to 25 on the high end. The next step is relating slope, let's call it S, to the difference between map distance and real distance, or M and D. D is the square root of quantity M squared plus E squared. E is equal to slope S times M. When you combine those equations, you get D is equal to M times the square root of quantity 1 plus S squared. The square root of quantity 1 plus S squared determines the difference between M and D. For example, a slope of 0.1 or a 10% incline results in a multiplier of 0.005 or 0.5%. A slope of 0.25 or a 25% incline results in a multiplier of 0.031 or a 3.1% increase. And a slope of 0.5 or a 50% incline results in a multiplier of 0.118 or just under 12%. I used Excel to determine and plot these multipliers for slope values between 0 and 1 in increments of 0.05. The plot is not linear. Between slopes of 0 and 0.2, the multiplier increases from 1 to 1.02. Then from slopes between 0.2 and 0.4, the multiplier increases from 1.02 to 1.077. So the greater the slope, the more physical distance deviates from your map distance. And this plot can be found in the show notes. So how does this help us? Well, at the very least, you can put this table or plot in your navigation notebook so you can estimate physical distance without performing complex division in your head or on a calculator. If you estimate the slope to be 0.25, the table or plot tells you to increase the map distance by about 3%. It makes the math much easier to do in your head. But it also helps you decide when you can ignore this deviation entirely. There's no universally accepted difficulty scale for terrain, but typically easy trails will have less than a 5% grade, and highly difficult trails will have sustained grades of 20% or more. For example, if the slope I'm walking is 0.25, the multiplier is about 3%. Over a map distance of 500 feet, do I care about an extra 15 feet? Probably not, especially if I stop at 500 feet to reevaluate my position. But what about over a mile of map distance? Does the extra 160 feet matter? Well, maybe in bush where I can't see the horizon or any landmarks to orient me. In those cases, a handful of feet might matter. But how true did I stick to my compass bearing in the first place? How accurately did I count my distance? I think effort would be better spent reducing error in those two factors first, and then worry about the deviation between map distance and distance traveled. Obviously, whether or not you choose to ignore the extra distance caused by elevation gain or loss should be based on your personal experience, the terrain and weather conditions, and your goals for the outing. Are you looking for an unmarked food or water cache, making precise navigation key? Are you looking for a cabin in thick bush that you can't see until you're standing on top of it? Most people will never be in those situations. So for most, land navigation is about using a map and compass to find a landmark or self-rescue, and terrain is the bigger factor. But even in those extreme cases, by the time the deviation becomes relevant, the slope is so severe that I'd rather choose an easier, albeit longer path to begin with. Thank you for listening to the STEM Sessions podcast. This episode was researched, written, and produced by Jarl Cody. Here at the STEM Sessions, we strive to share accurate and complete information, but we also encourage you to do your own research on the topic we discussed to confirm the accuracy of what we've presented. Corrections are always welcome. Show notes, contact information, and details of our other activities can be found on our website, thestemsessions.com. If you received value from this episode and wish to give some back, please visit thestemsessions.com/value for value for ways to support the podcast. Finally, please remember STEM is not a tool exclusive to experts, policymakers, and talking heads. Every presenter is susceptible to unconscious and sometimes deliberate bias, so always verify what you read and what you're told. Until the next one, stay curious.